Okay, so in this video, we're going to start talking about something new. I'm going to briefly introduce the idea of generics and templates in C++. Okay, so one of the key goals of the C++ language is to make it easier to reuse code. And there are actually lots of features in the language that help with this. One of them is class inheritance. We're going to be talking about that next. And the other are generics and templates. And generics write code that is independent of the data type. Normally, when you look at C or C++ code, you're always labeling everything with a type. And what that means is you get locked into using certain types. But it would be nice if you can actually write code in a way that's independent of type, and then it just works no matter what type you give the code. And that's what we're going to achieve with a template. So just as motivation, suppose I want a function that picks the greater of any two values of the same type. I could write this out for integer like this. I could, have a function called max. If I pass in a and b, they're both integers. And if a is greater than b, I return a, else I return b. And what's wrong with this? Well, there's nothing wrong with it except that it only works for int. It doesn't work for any type I have, right? But I would like a function that works with any types, with any type that I have. Now I could use function overloading to help me out, and I could write a version of max that takes integers, I could write a version of max that takes characters, and I could write a version of max that takes doubles. And that's great, and this will compile, and this will work, and the compiler will figure out which function to use in most situations, but it's pretty tedious. I mean, for every time I find some new type, I'm gonna have to implement a new function like this. And who knows how many more types I'm gonna need. So this isn't really good enough. And if, let's say I want to use this function on objects, I'll have to rewrite it again for objects. So this is not generic enough. This does not save me much effort. It really creates work for me if I have to create all these different implementations for all the different types. So here's what I really want to do. I want to be able to write some code that says the return type and my two arguments can be anything. But they all have to be the same thing, but they can be anything. And then whatever they happen to be, interpret the code in that context. So anything could be int, and so everywhere I wrote anything here, it could become int, all the anythings could become double, all of them could become float or character or string, whatever they become, this code would then compile and work. That's what I want. Well, amazingly enough, we can do that with C++. What we have to use is we have to create what's called a template. And we have to use the template keyword. And so this template keyword tells the compiler that this is a pattern for how we're going to make some code. And the pattern is going to be specialized by a type name that we call anything. And you have to put this in brackets, okay? This isn't just like something I put on the slide to help it make sense. This is the real syntax. You say template, less than sign, type name. Anything can be an identifier, any kind of a legal identifier name. Type name is a keyword, anything is an identifier, and then a greater than sign. And then everywhere we put anything in this code below, the compiler can substitute it for some type that it thinks would be helpful. Okay, so this is just like the code we wrote, but now the anything type is in fact a variable. It's something that can change in the code. I don't mean variable in the sense of it takes up memory. I just mean variable in the sense of like a, from a mathematical sense, an abstract sense, that now this is something we can tune. This is something that can be changed in the code by the compiler. I can clean up that code a little bit just to make it look a little bit better. It's common to use a terse type name, often just T, to stand for type. And although any legal identifier name works, so you'll often see templates written like this: template, and then type name T. Since it's a type, we just use a very single capital letter to reflect that. And then this return type T, and this argument type T, and this argument type T should all be the same type when the compiler decides to use this function. Okay, and just to get it out there in advance, you can also replace type name with class. But they mean the exact same thing. It doesn't have, this type doesn't have to actually be a class. It's just a way of saying this is some type that I care about. You can even declare templates with multiple arguments. The ones I just showed you, we said template and then type name T, so there was only one type, but I could actually have multiple types. And those types, those arguments here don't have to be type names. We don't have to be parameterizing on the type alone. We could also be parameterizing using an integer. So for example, if one of my arguments is an integer n, then I could write some loop in my code that uses n, and that n is actually a constant, because when whatever I specify in a template, it has to be decided at compile time. And so this value n has to be decided at compile time, not at runtime. So it's not something that can change when the program runs. That n becomes fixed in the code. And so this n in this case would be 5. But I just wanted you to know there could be multiple arguments. We're not going to talk about that a lot at first, because usually our templates are going to have one argument. Okay, so let's come back to this max example. And we have our template called max that's based on type T. And then based on this type T, it'll determine if A or B is bigger and then return the one that's bigger. Okay, so now in main, I'm gonna print out a couple of different values. One of them is based on the max of 34 and 55, and the other is based on the max of 3.14 and 2.7. Well, in this first case, the compiler realizes that I wanna call this function max. And it looks at the types and it says, oh, those are integers. And so what it does is it realizes that I want the version of this function that expects integers for T. So everywhere I have T here has to be an int. And so the compiler then realizes, oh, it can use max to handle just integers, and it generates a version of the function that will just operate on integers and calls that function, and then correctly will return 55. And then in the second case, it realizes, oh, I passed in 2 doubles. And so in that case, it makes a version of max that's based on double, and generates the suitable code. It'll have a return type of double, 2 arguments of double, and then compare doubles, in this greater than operator. And so then at runtime, it'll call that function of that version of max that's specialized to doubles to produce the answer 3.14 that we want here. Okay, so in summary, templates allow us to write algorithms and even objects once and then reuse them for many different types of data. Templates rely on the compiler to deduce the correct type to use. And so anytime you want to write code or a data structure, an algorithm that would work the same way on a lot of different types, like integers, characters, or doubles, then a strategy you might want to use is a template and specify that type can be changed out in multiple different ways, right? That type can be changed out, and that the code will still be meaningful regardless of the type that's being applied. And then the compiler figures out what type you're using and generates the right type of function for you based on the template pattern.